right, so in today's video, we're going to set up an acceleration structure. If we're ray tracing, we want to be able to handle large data sets, and it handles it really badly unless we put in some sort of acceleration structure. So to start with, I'm just going to give an idea of performance. So we have this program, and I want to modify it so that I'm also logging out how long the render took. So here we'll have our blank canvas label, then we'll have the canvas, and I'm just going to declare two parameters. Those are the sphere count Okay, cool. So let's work on the sphere count first. So I want to sort of automate this a little bit more. If I go to the source file and then the main, I'm going to declare a sphere count here. We'll go const sphere count, which is a number, and I'll just give it some value like 64, for instance, and then I'll pass that in as a parameter when constructing the scene. Now I don't need to pass it in for the renderer because the renderer has the scene already. It can query how many spheres are there. As a matter of fact, if we go to the renderer class, just as a refresher, and yeah, that's fine for now. I'll just build it in a second. If we look, actually I should probably build it now, just to install the dependencies. That's fine. I'm expecting an error, but now we have the WebGPU dependencies. Anyway, so if we go down to the make assets, create assets, we can see that we are already, for the sphere buffer, we are already querying how many spheres are on that list. So we don't need to change that at all. That's going to work fine. What we do need to change is the scene. So I'll just go to the scene, and then I'll take in the constructor and take that, use it to set the size of, use it to set the size of the number of spheres. Now I'm just going to change this as well, because in my program I'm going to make a really large scene. So I want these to be ranging from -50 to +50. Sometimes behind the camera, that's fine. Okay, excellent. So the scene is set up. We'll tell it how many spheres to make. It makes a whole bunch of them. That's fine. Now I'm going to go back to the renderer. Oh, wait, no. Actually, let's log out the number of spheres on the web page. So we'll say, okay, call this sphere count label, and that will be a HTML element. Something like that. I just, why not make it big? Okay. All right. So anyway, so we just grab the label and then we populate it. So we say, okay, sphere count label inner text. We'll get the sphere count. So I'll just run it now and check that it's doing something. Okay, and then just run this. Okay, so it looks like we're having an error. Weird, no worries. Let's just go inspect. And the error is over here, generated while compiling the shader. Okay, so there's nothing wrong with this. It's the shader. Weird. It says it's this screen size. It's having trouble converting this unsigned integer to an integer. No worries. So I'll just head over to the Raytracing kernel, and that said line 37. So we'll just go down. Okay, and I'm going to do the same thing as I did here, which is just take this and use it as a constructor. So I'm explicitly casting it, and now this should be fine. So I'll just close that down. There we have it. Okay, so we are seeing spheres. That's good. We just need to display how long it took to render them. So what I'll do for this is I'll just hit the back button, and that'll just put me back to some page, just so I'm not burning out my GPU needlessly. And I'll go over to the renderer. It's not prepare scene, it's down here in the render function. So the first thing I'm going to do is get the start time. And the way we do that is there's something called performance, and we go performance now. That returns a number, and it's milliseconds of some sort of internal clock. So we get the start time, we go right down here, and then what we want to do is get the end time. Fair enough. And then subtract, and that will give the render time. But remember that all this is doing is setting up a bunch of work for the GPU to do. And this is an asynchronous function. So when we call this queueSubmit, it sends it off to the queue. And that can happen really quickly. But the render, which occurs on the queue, could take quite a bit longer. So what we want to do is we want to, if we were in Vulkan, we would wait for the queue to idle and then time it. But another approach is go this. Well, I mean, the reason we need another approach is that we don't have something like wait idle. We don't have it. But we do have this on submitted work done. So this is a promise, and the promise is resolved at the point where all of the render is done. So what we do is we call then, and then the argument which comes in here is the function that we want to perform after this promise is resolved. In other words, after this submitted work is done. So I'll just make an anonymous function, which is pretty much this. So this is just ensuring that the timing is done after the render has completed. Okay, so now what I'll do is pretty similar to the main. So I'll just grab, I'll call this, I'll call it performance label. Okay, so get, that was render time, was the ID I had there. Okay, and then I'll set that text. Okay, so I'll take the render end time minus the render start time. That's the time difference. Cast it to a string, and there we have it. Okay, so I'll just restart the server, and click back over, refresh that, and now we can see that we are timing our renders. It's a little hard to see, it's a little horrendous, but performance is pretty good. Currently we've got 64 spheres, a lot of them are behind us or above us or below us. We're rendering at, yeah, quite decently, 5 milliseconds per frame or something. So a fun exercise is to keep dialing this sphere number up and see how that affects performance. But just as an example, we can go back. Oh, my laptop's not overheating. That's good. And just change this number to, I don't know, about 512. Let's see what that is. Actually, yeah, let's do that. Okay, change my mind. So we'll just end the server, start it again. Okay, still pretty good. We're still at about 7, 6, 7, 8 milliseconds per frame. What happens if we dial this up and double it? Uh-oh. Now we've gone from 7 milliseconds up to 120 milliseconds, 130. That's really bad. So you can see that it's getting more and more important for us to have some sort of organizing data structure here. Just out of interest, I'll open up I'll show you the results that I've got. Why can't you just open a new, is it that hard? I have to click through all these different, okay. So let me go spheres, and I'll call this the brute force method because that's what it is. So like I said, my trial that I like to do is just doubling the sphere count each time. So I ran this before. Honestly, I'm surprised, impressed that my machine is able to handle up to 8,000 with brute force, because the results get really bad. But more or less, I found that it took 2 milliseconds for one sphere, and I'll just fill this in. Actually, don't save. Okay, so as you can see, performance starts off pretty good and then gets really bad. And there is an element of randomness to this. There are some configurations which are easier to traverse than others, but this is brute force, so we really have no insurance at all with this performance. Okay, so we've got it so that we're timing how long our render takes. Let's construct an acceleration structure and try to speed it up. Okay, so before I launch into the full coding example, I want to briefly talk about the concept. Imagine that we have our scene of some sort and we're looking down on it from above. And we have a whole bunch of spheres, so one over here, maybe one over here, and one over here. I'll just label these. So we'll go A, B, C. Now, if I were to shoot a whole bunch of rays through here, like just imagine we're looking down on it and there's a whole bunch of rays shooting through. The majority of these rays are going to hit absolutely nothing. But what we're doing right now is, even for, say, this ray over here, we're still testing it against all of these spheres because we don't have any semantic meaning about our scene. We just know about things. So I'll just get back. Okay, so what I'll do is I'll say, okay, first of all, we have a bunch of spheres. And I'll just denote that as some sort of array. So we have sphere A, B, and C. And what I want to do is I want to grab these spheres and throw them into groups, but it might not be the best idea to rearrange the spheres for just whatever reason. So what I'll have is I'll have a lookup table, sphere indices, which at the moment is just in the regular order. So what this is saying is the first one of these is referring to sphere 0 and so on. So now what I'll do is I'll grab all of the spheres and I'll bound them. So if I look at the leftmost sphere, we have that x coordinate. The rightmost, we have this other one. And then in the y, we have the top and bottom levels. Okay, and I'll call that node 0. And then I want to subdivide that node further. So then I'll say, well, which dimension is larger? In 2 dimensions, it would be the x dimension, which is the larger extent. And so we'll sort of split along this axis here. Everything to the left will go to some node. Everything to the right will go to some other node. So if we look at B, B is on the left, and we want to constrain that node as tight as possible. So I'll call this node 1. And then if I look at A and C, they're on the right. So I put them together and constrain as tightly as possible. Okay, so that's node 2. So if I were to look at this as a tree of some sort, it's going to be a tree. We'll have node 0. That'll be an internal node in the sense that it doesn't have any renderable objects, just references to other nodes. Its left child is node 1. Its right child is node 2. And then if we look at node 1, node 1 will have, let's say, 0 as the sphere index. And node 2 will have some spheres indexed 1 and 2. So this is a little strange. So at the point where I construct the tree, I'll need to rearrange the sphere indices. And this is the benefit. I can rearrange the sphere indices without touching the data structure that they're describing. So all I would need to do is swap around these indices. And now if I look at node 1 and I say, hey, what is your renderable object? It's index 0. So then I look over at sphere indices. Index 0 is thing number 1, and I use that as an index into the spheres array, and that's sphere B. For sphere 2, it has 1 and 2, so I look at positions 1 and 2 of the sphere indices and use those to reference in, and those are the spheres A and C. So I know that's a little strange, but I just wanted to go through that. So again, if I were to look at the node structure, okay, so what am I thinking? So I want to have a compact way to represent this. I'll put L for left child and store that as 1. And I'm actually not going to store a number for right child, because I'm going to go with the convention where the right child is always 1 more than the left child. I can totally do that when I build the BVH. And then if I look at node 1, I'll say left is 0, and I'll put C for count is 1. And because, okay, so then I'll also put here count is 0. So this is indicating that node 0 has no renderable objects. It is an internal node. Node 1, on the other hand, has 1 renderable object. We can see that there. And so that is assigned to interpret L as the index of the first sphere. Similarly, the index of the first sphere here is going to be 1 and count is 2. Okay, so it's all based around the count index, the count variable. If it's 0, it's internal, and L is the position of the first child, left child. If it's non-zero, then it's external, and L is the index of the first sphere, and C is the number of spheres. Anyway, so just so this makes sense, I'll go through a bit more examples. So let's have a look at some rays. So let's say we have a ray which comes across and intersects that sphere. So I'll say, okay, call this 1, and I'll say, okay, for ray 1, what do we do? Well, the first thing we want to do is check against node 0. We say, are we going to hit that box? And yes, node 0 is that whole area. So yep, we're going to hit the box. So because we hit the box, we then check the children of the box. So we say, okay, node 1 and node 2. Node 1 is a hit. Node 2 is a miss. So then we'll repeat the process searching node 1. Okay, what about, I don't know, what about a ray that goes through and hits nothing? So we'll go ray 2, node 0, hit, 1 is a miss, 2 is a miss, so exit, do nothing, do nothing. Okay, fair enough. What about some nodes that hit both of them? So let's run a node through here. I'll call this node ray 3, ray, not node. So if we look at ray 3, of course, node 0 is a hit, node 1 is a hit, node 2 is a hit. But I'm going to set this up in my rendering loop so that I'm only searching one node at a time. The closer of the two nodes is node 1. When we make the intersection function, we can make it so that it returns the distance to the node. So what we'll do is what we'll do is a little search and store. Why? What's wrong with this pencil? Okay, so what we'll do is node 1 will note, we'll take that as the current node that we're going to search in the next iteration of the loop. Node 2, we're going to just store it on a small array. And later on, if we miss node 1, we can always go back and search node 2 again. And if we hit node 1, then we'll store the distance to that hit. And then we can use that to maybe prune node 2. But anyway, let's go back the other way. So if we were to go in the reverse direction, we'll call this ray 4. 0 is a hit. Both 1 and 2 are hits. But in the intersection code, we return the distance to the closest point on the box, basically. So we can query and check that node 2 is the closer. So we'll search that one first, and we'll store node 1 so that in future we could search it after we've done everything else. Okay, so that is the basic concept, some of the terminology. Let's start implementing it. Okay, so let's head into the shader. We'll just go to the Raytracer kernel here, and I'm going to, we're going to work on the shader for a bit. One thing is I will add maybe just down below the sphere, I'll add a node. Now, with the sphere, just the same way that we took advantage of alignment by packing the color and radius together, a vec3 and a float, I'm going to arrange this around vec4s. So the node is going to have a minimum and maximum corner, both of which will be vec3s. And because of alignment, this will actually reserve 8 floats. You'll have, 3 floats here plus 1 float of padding, and then 3 floats here plus another float of padding. So what I can then do is take advantage of that padding and sort of pack this together. So we'll have the left child. Now really this will be an integer, but for whatever reason, I have always had mixed results with integers in shaders, so I'm just going to keep it as a float. It's a bit of a performance hit, but it is what it is. So then I'm going to have the sphere count, which would be a float again. Okay, and now I want, just the same way that I had a sphere and then a collection of spheres, I'm going to make a collection of nodes. I'll call it a BVH, and we'll have nodes, which will be an array of nodes. Okay, excellent. And then I'm going to need the set of object indices. So I'll just declare that. Excellent. So no worries. I'll just go down to the section where I'm declaring my bindings, and I'll declare these as my bindings. So we'll have now binding 3 and 4 also taken up by storage buffers, and binding 3 will be the nodes, so I'll call that a tree, and that will be of type bounding volume hierarchy, and then binding 4 will be the, I'll call it sphere lookup, and that will be the object indices. Okay, cool. So I'll have to declare that on the code side, but there it is. Now, what I will do is just go down to the ray color function, and I'm going to modify this a little bit. So what we're doing is we set up all of our state, but I also want to have I want to start tracing the bounding volume hierarchy. So I'll make a variable called node, which is an instance of the node struct, and I'll look into that. I'll get tree nodes 0, so just the base node. Then I'll have a stack where I store the nodes that I want to explore later on. So that will be an array of node type, and for the size, just any constant value, probably not too big. I'm going to go with 15 in this case, because if I look at 1024, that's 2 to the 10, then 2048, 2 to the 11, 12, 13, 14. I think it's 14. I've just added one more, so 15. Typically, the stack will grow in proportion to the log of the number of spheres or objects, base 2. So then I'm going to keep track of the stack location. That'll be an unsigned integer. We'll start it out at 0. So what this will be doing is remembering what was the position in the array of the last thing that we're about to explore next, if that makes sense. Now I'll start exploring I'll leave this stuff for now. Right, so what I'll do first of all is I'll just get the current node, read out its contents and convert them into unsigned integers. So I'll say, okay, sphere count. Okay, so I want to know this node that I'm exploring right now, is it internal or external? And I can do that based on the sphere count. So if sphere count is equal to 0, if it is, then treat this like an internal. Otherwise, treat it like an external. Now, what do we do with an external node? We do all of this stuff. We look through the underlying spheres. So I'm just going to copy this right now, or for now, and just put it inside, and I'll worry about that later. Okay, so what do we do if we have an internal node? Well, we want to explore the left and right children. So I'll set this up. Remember that the contents variable is multi-purpose. If it's internal, then it is the position of the child nodes. And if it's an external node, then it's the start position of the sphere indices within the chunk. But anyway. Going with the convention that the left child plus 1 is the index of the right child. Okay, so I haven't written this function just yet, but let's pretend that we have a function which takes a ray and traces it towards an AABB, axis aligned bounding box, and indicates the t parameter along the line, the distance to hit that box, more or less. So I'll say, okay, distance 1. And I'll say, okay, well, I'm going to call this function hit AABB. I'm going to pass in the ray and the node that I want to test against. Okay, so this distance will represent the closest distance that the ray has to travel, the first point of intersection. And I want to organize these nodes so that I'm searching the closer one first. So I'll say if the distances are reversed, so distance 1 is greater than distance 2, then I'll swap the distances and the nodes. There we go. So I'm setting it up so that distance 1 will always be the closer box. Okay, so if distance 1 is the closer box and we want to reject anything which is further away than this, where are we, nearest hit parameter, then we can test that. We can say, okay, if distance 1 is greater than nearest hit. Well, in this case, we've missed everything. So when I write this function later on, one indicator that the ray is going to completely miss the box is just to return a really large number. So that's sort of what I'm testing here. Well, okay, so I'll do a check. If our stack location is 0, then we have no further boxes to explore and we are done. So we can break out of the loop. Otherwise, we'll say stack location, reduce it by 1. yeah, reduce it by 1 and then get the next node, which will be explored. So this is the case where the ray just completely misses everything. Now, what about the other case? Well, if distance 1 is less than nearest hit distance, then we definitely want to check distance 1. And it is a smaller distance, so that's why we want to check first. So I'll update the node variable so that it points to child 1. And then in addition to that, I want to test, should I also check child 2? So the test there is if distance 2 is less than the nearest hit parameter, then let's store that as well. So we'll say pop that onto the stack. And move that stack forward. Okay. Excellent. All right, so we've done all of that. Those are all the tests we need for an internal node. I'll just go through that again. So if we get an internal node, no worries. Extract its two children, the left child and the right child. Get the distance to each of them. Make sure that child 1 is always the closer node, so swap things around if we need to. If the smaller distance is just not going to work, then obviously the ray is going to miss both of them. So just either exit the loop or grab the next node to process, because we're done with this one. However, otherwise, child 1 can be explored. So it is stored into the variable node and potentially store child 2 to explore as well. Anyway, that's it. So if we get to this point, then we are on an external node and we have a bunch of spheres that we want to test. By the way, there are some advantages to writing if-else. There are some advantages to writing if-else code in shaders, because shaders operate, or some shaders operate with what's called SIMT, which is single instruction multiple threads. It's more of a modern GPU thing, but I have found that occasionally I'll improve my performance by writing an if-else explicitly. So let me just go through here. So if we get to this point and everything is fine, then we'll go, okay, start at 0 and go to the sphere count. I'm just going to modify this as well. With WGSL, it does not support function overloading based on operands, so arguments, so I'll have to just name the functions appropriately. So I'm going to send in my ray. I'm going to go, okay, objects, spheres, but then the index of the sphere is, I'll get the sphere lookup. So remember that contents is the position of the first sphere. So take I as like an offset from the first sphere. So I pass this in and I'm saying, hey, I want sphere number 10 or something. And sphere lookup, because these spheres have been jumbled around by the BVH construction, sphere lookup will say, okay, thing number 10 on my list, that is referring to sphere number 7 or something. And it's this level of indirection which we're applying here. So for the near distance, we don't want anything closer than this. We don't want anything further than nearest hit. That should be fine. So then I'll just bring this over, maybe bring all of that over. There we go. Okay. So I'm just going to run through that again, just double checking everything. So if we have an external node, then we will look through and say, hey, test against all of its spheres. We will repeatedly test against each sphere, and if we have a successful hit, then we'll store the information that we need to store. I'm just going to quickly check this. Okay, that, and then this is the, okay, good. So then if we get to the end of this loop, oh, there's something I missed. That's right. There is something I missed. Of course, after we check something, we will either be done. So we'll say if our stack location is 0, we have no more nodes to explore. We're done. We can break. Otherwise, we have got another node to explore. So we will decrement our stack location and then load the next node. Right, and now we're really done. Okay, so I'll just go down, and this is the hit function. I'll just rearrange that hit sphere. It's been renamed. Now I want to write the AABB intersection code, but this is a little conceptual, so I'll pop over to my whiteboard and we'll have a look through it. Okay, so how do we intersect or test for intersection with an axis-aligned bounding box? Let's look at a 2D case. So here's my box, I guess, something like that. And I'll have a look at the we'll have two really important points we care about: the minimum point and the maximum point. The difference between those defines an extent, which is the length and width, or in 3 dimensions, length, width, and height. So imagine that we're looking at the x minimum. That's everything down here, including that line. And then we look at the y minimum. That's the minimum height, so everything along there. And we have a ray. We'll just keep it nice and simple. So the ray's coming along, and it's going to intersect here. And I'll call this, I don't know, x star, y star. The ray will have some direction, dx, dy, and will have come from some point, x naught, y naught. Okay, so let's look at the x dimension. So we have that the position on the ray, x coordinate is equal to x star, and that has come from the ray's origin plus the direction times the parameter t. And it's easy enough to rearrange this and say, oh, well, okay, so t should be the target minus the origin divided by the direction component. And then, well, it's the same for the y dimensions. We have the y target minus the y component of the ray's origin divided by the y component of the ray's direction. Okay, so then the question is, how do we interpret this? Because we're getting 2 different t values. But think about it as this t value here is the value of t that we need to be within the range of the box. And the value here is the value that we need to be within the y range of the box. So in this case, they're both equal and it doesn't matter. In this case, just pop through here, we would have some sort of, well, this is intersecting the y. So now at this ty, it's easy enough to accidentally turn this thing into a rubber, but there's no way to accidentally turn it into a, yeah, auto minimize. That's probably what you want, right? Jeez. Okay, all rage aside. So this point is the point at which we intersect in the y, come into range. And here's where we intersect in the x. So which of these parameters do you think we would take as the intersection point? Well, it's the larger of them. So when we're approaching a box, we always pick the larger of the minimum coordinates. Now, similarly, if I go up here, we have tx, ty. Here, ty is larger, so we will select that as the first point of contact with the box. Okay, so that's all well and good. The next question is, how do we test if we hit or miss a box? So let me just give an example. We have this box here, and we'll go x minimum, y minimum, x maximum, y maximum. Okay, now I'll draw two rays. One ray will hit it and one ray will miss. So we'll go like this. Ah, that's pretty cool. And then we'll go like this. Oh, that one didn't. Oh, anyway, it's fine. It's fine. Okay, so actually I will continue that further. Okay, so let's look at the ray which hits. I'll put a minus here to indicate that this is a value for t minimum. And then another one, it's another value for t minimum. So, all right, here, this is t minimum is always the larger of the values. Then we come back in from the other way. This is on the maximum side, so intersecting with y max and x max. And we always pick the smaller of those. So here we have t minimum, t maximum, and the ray is going along this way. So t minimum will be less than t maximum. In the other case, okay, so this is x minimum, so we'll intersect here. This is y minimum, so we'll intersect here. And then we choose the larger of those as our t min value. And then for the maximum, we have y maximum, x maximum. So we'll pick this one as t max. And the ray is going this way, which means that t max is actually less than t minimum, which is sort of messed up. So our test is, once we find the maximum and minimum t values, then if the t min is less than the t max, we have successfully hit the box, and we can return t min as the parameter for the distance to the box. Otherwise, it fails. And there's another case, and that is if the ray is going through the box, but it's behind the viewpoint. So remember that here we have t equals 0. In this direction, we're looking forwards. Our t parameter is positive. Backwards, our t parameter is negative. So it doesn't matter if t minimum is negative, because you can be inside a box and looking out from the inside. The thing behind you is negative, but that's fine. The issue is, because t max corresponds to the point furthest away, if t max is negative, that's an indicator that the box is completely behind you and to ignore it. So anyway, with that in mind, let's get in and code this up. All right, so back to the ray tracer. I'll just go right down the bottom and we'll write the bounding box collision function. So we'll say, alrighty, this is a function called hit AABB, and we'll take array and a node. And this will return a float, the parameter along the ray of the intersection point. So what we want to do is we want to divide the let me write this. So I'll say, okay, make a variable called t1, take the nodes minimum corner minus the ray's origin, divide by the ray's direction. So because of the wonder of SIMD, SIMD with shaders, what this will essentially be doing is individually dividing into each of the dimensions. So we have the x separation, divide by the x direction, the y separation, divide by the y direction, and so on. And this works just fine, but for whatever reason, multiplying is more stable than dividing. It's a little bit weird. This might just speed things up a little bit. So I'll just make this variable inverse direction. Now I know what you're saying. Aren't we dividing here? Well, yeah, we sort of are. That's an interesting point, but let's just do this anyway. Okay, so what this will essentially do is give off all the set of t values that we would need to intersect with the minimum corner of the box. And we'll do the same with the maximum corner. However, just because that is intersecting the minimum corner doesn't mean it's the closest corner. The box, the ray could be coming from the other direction. So let's change that to T2. So what I'll do is I'll define a variable called tmin. And that will be the minimum of T1 and T2. And the way this function works is it will be an element-wise minimum. So it's possible that, what am I thinking? It's possible that some of the, what am I thinking? The minimum corner, you could be looking one way and it is straight up the closest thing to you. You could be looking the other way and it's the furthest thing from you in all directions. But then you could be somewhere between that, where in the x dimension it's the closest, but then in the y dimension it's the furthest or something. So this will just pick out from all of the three elements of T1 and T2, which of those is the smaller. And then we'll do the same thing. So in each dimension, this is telling me the smallest distance along the ray that I have to move to get within that dimension, within that range. So now I want to boil this down to a single float. So remember what I was doing before with all of the minuses and the pluses. I'm going to break a few rules here with creative variable names, but that's fine. Or at least it has to be fine because this is how I'm doing it. So what I'm doing is I'm calling maximum twice to get the absolute maximum of all of these. Remember, the minimum value can only increase. If we go any further back along the ray, we will be violating some other dimension. So then for the T maximum, similarly, that'll be the minimum. There we have it. Okay, so back to the example I was doing before. Imagine that I've gone through all my sets of minuses and picked the appropriate T minimum and appropriate T maximum for the pluses. Now I want to check if I've completely missed the box. So if T minimum is greater than T maximum, in that case I want to return some value which indicates that we've completely failed. So I'll just go 1, 2, 3, 4, 5. This is a really bad. This is bad. And the other test is if we've hit the box, but it's behind us. So the closest thing along the ray is actually negative. We'll fail in that case too. But anyway, otherwise, we can return the closest distance to the box, which is t minimum. Okay, and there we have it. So now what I want to do is head back to my code and start working on maybe the scene. Well, actually, I changed my mind. I'm going to go to the code and make a file. I'll call this node.ts. And I'll just define my node here. So I'll go with the same convention that I had before in the shader. I'll go minimum corner, left child, and sphere count. Okay, now both of these are going to be vec3s. So I just go vec3. We can see that's from GL matrix. If I click this, I will now import that. And there we have it. So no functions here. We'll just be using this in just as a data store. So we'll just go to the scene. And I think all of this is fine. So we have all of this stuff. In addition to this, I'm going to have a set of nodes, which we should probably import all of this. So we'll go import node. And so I can do some math stuff. So I have the array of nodes. Then I want to keep track of how many nodes have actually been used. And then I also want to keep track of the lookup table. Okay, so that is fine. I'll just pop down here, and after I've made everything in the constructor, I will then have a function called build bounding volume hierarchy. Okay, so I'm going to have to set a few things up. I will set up the sphere indices. And I'll just set this up with an initial layout of no reordering, just a one-to-one mapping to the spheres. Well, it'll always be a one-to-one mapping of the spheres, but an identity map, if that makes sense. Okay, and then I'll set up the nodes. So what I'm doing here is, it turns out for a binary tree, the theoretical maximum number of nodes, if we want to have, I don't know, if we want to have n children, the theoretical maximum number of nodes will be 2n minus 1. What I do need to do is construct an entry for each of these, just a dummy entry. Later on, when I refer into this, it might say, hey, that's undefined. So we allocate the space and fill it with a whole bunch of nodes. Okay, so let's keep going here. We'll say make a root. Okay, so at the moment, root is holding all of the spheres. Remember that when sphere count is non-zero, the left child is actually referring to the index of the first sphere. So we start at sphere 0 and we hold all of them. So what I want to do is I'll write a function which updates the bounds. So I'll update the bounds on node 0. That will grow the node so that it tightly packs all of the spheres. And then what I'll do is write a function which subdivides that node. So just like I was saying in the example, it will look in each of the dimensions, pick the larger dimension, split that in half, and then sort the spheres so that they're in the individual halves. Okay, so let's have a look at the update bounds function. We're going to need to take the index of the node that we're working on. Okay, no worries. Okay, so what I'm going to do is I'm going to set the node up with some impossible values for its minimum and maximum corners. These are the coordinates in the X, Y, Z. So I'll say, okay, set the minimum corner to 2, 3, 4, 5, 6. And likewise, set the maximum corner so that everything we see will be bigger. Now what I want to do is loop through, look at each sphere inside that node and adjust the bounds. There we go. Remember the rules here. If we're looking at something with spheres, then left child is the index of the first sphere. And that has to go through the sphere indices lookup table so that it's referencing the correct sphere. So what I'll do is we'll just make a variable which will be useful later on. So what I'm saying is if I take the center coordinate and I add the radius in every dimension, that will be the maximum corner. And if I subtract the radius in every dimension, that will be the minimum corner. And because that radius variable is showing up so much, it's useful just to have that as a variable that we have access to. So keep going here. Okay, so we'll subtract the axis from the center and store that into the temp variable. And then we'll set it up so that the minimum corner is storing the minimum of what's already there and the temp variable. Then we'll do the same thing with the maximum. And there we have it. So by the time this loop runs, the box will be tightly constrained around the spheres inside. Okay, so now let's have a look at the subdivide function. But this is a little bit, it's not super tricky, but it's something that's good to work out on paper beforehand. Okay, so the big concept here is that I need to be able to take a bunch of things and sort them according to some criteria. And the sorting algorithm I'm going to use here is in-place quicksort. So I'll just do an example of how this goes. Let's say we have a list of numbers. I'll go 0, 2, 7, something like that. And I have some value like 6. So I'll call 6 my pivot. And the sorting criteria will be, I want the numbers less than 6 to be on the left and the numbers greater than 6 to be on the right. So what I'll do is I'll have two locations that I'm looking at, the start and the end. And my criteria is everything to the left of the start is less than 6, everything to the right of the start is, I don't know, greater than or equal to 6. So the way this works is I look at this position on the left and I say, this number here, is it bigger than 6? And it's not. So we'll progress to the next one. And the position on the right doesn't change. So the same thing again. The same thing again. 2 is less than 6. We go here. See that everything to the left of our position here is less than 6. Now we look at 7. Is 7 less than 6? No, it absolutely is not. So what we can do is swap that with the number on the end position. So here we have 12 and 7. We've swapped them. Now we have a guarantee that this number is bigger than or equal to 6. And so the right position can move forward. We're happy with that. Now we need to check 12. And as you can see, 12 is too big. So we'll go ahead and swap it with what's on the right. Oh, oops, swap it, I said. Okay, so we potentially have swapped something dodgy into this position, so the left position doesn't change. But because we swapped, we now know that that number is bigger than or equal to 6. So from here, it's just going through and checking. So we check 2, 2's fine. We check 3, 3's fine. Then we find that our left position matches our right position, and we are done. That is the sort. So that is really the heart of this subdivide. We have our sort of box wherever we are, and we look and we see which dimension will be split. It's the larger dimension. Then we get some split position, and then we'll have a whole bunch of these things. We need to sort them so that some of them are in one box and some of them are in the other. Okay, so let's go in and implement that. Okay, so let's get this show on the road. Okay, so what I'm doing here is just providing an early exit. Well, providing an exit case, because this is going to be a recursive function. Subdivide will call subdivide. Extent will hold the length, width, and height of the bounding box. And yeah, it is what it looks like. Axis is the dimension along which we want to split. So we're just going to tentatively start it at the x-axis, and then we'll say, all right, well, if the width is larger than the length, then the y-axis becomes our split. And similarly for the z-axis. Okay, so now I just want to find which coordinate along that axis should we use as our splitting criteria. And the way I'll do that is I'll take the minimum corner plus half of the appropriate size. So half the width, half the length, half the height, whatever it turns out to be. All right, so now I'll start my in-place quicksort. So I have my starting, my left position, which will be the position of the first sphere within the lookup table that this node owns. And then for the j, I'll have I plus account minus 1. So each node will own some subpart, some little subpartition of the lookup table, and this is setting up the start and end positions of that range. Okay, so the first thing I'll do is I'll check the sphere under position I, see if it should be swapped. Actually, what am I saying? See if it shouldn't be swapped. It would work the same way otherwise. Yeah, but on the else branch, I'm going to swap the I and j. Good, so that's swapping the entries in the lookup table. It's going to jumble the table up a little bit. It's fine, that's what we expect. Now, what I want to do is I want to register, after this is performed, I want to register how many spheres are in the left child, how many spheres are in the right child. Okay, so remember, I initially starts at left child and travels away from it down the array, if that makes sense. So if I just track how far it's traveled, that is the number of spheres which are in the left child. Now, in the degenerate case where all of them were in the left child, that's a little cringe, but it's okay. We can just return, we're done, we don't need to subdivide further. Okay, so I'm just tracking the index of the left and right children, which we're about to create, about to set up. And each time we need to increase the number of nodes used. And this is also ensuring the convention where the right child is always one more than the left child. So now what we can do is go ahead and set up both the left and right children. Okay, great. So we have partitioned the spheres into the two different boxes. Now what I need to do is just set up the original node. So what I'm doing is now that I've subdivided it, I'm turning it into an internal node and making sure that it points to the child which was created. So all I need to do now is update and subdivide each of the children. Okay, and fingers crossed that will create the BVH, the acceleration structure. That's what we need. Okay, so now what we need to do is just head to the renderer and make sure that we've created everything. So we'll need to go back over here, and you may remember when we were making the shader, we declared that we were going to have a whole bunch of storage buffers. So we'll need to declare those over here. So I'll have a node buffer. And now I need to create those. So I'll just go down, close this, set up device, that's fine. Make pipeline, we'll look at that later. Create assets, okay. So here we are, making the sphere buffer. Let's adapt that code. So I'll have the node buffer descriptor. It still is going to use 32, it still is going to use 8 floats per thing. But we're going to go nodes used, use that for the number of elements. This is all fine. Now I'll just go node buffer. Then I'm going to create the sphere index. So that will use 1 float per sphere. The rest of that is fine. And we'll just create the sphere index buffer. Okay, cool. So at this point, we have created a whole bunch of storage buffers. We will now need to declare them in the pipeline bind group layout and just the bind group itself. So we'll just go to make pipeline. Now in here, we're creating the bind group layout. We don't need to declare much here. We just need to declare that we're going to have a few more storage buffers. We don't know what they are yet. So I'm just saying, all right, so binding number 3 will be some sort of storage buffer, read-only, used in the compute shader, and binding 4, the same thing. Okay, so that's fine. I'll just close that. And now we'll go to the bind group itself. So this is where we refer to the actual buffers. Okay, so for binding 3, that will be the node buffer. For binding 4, that will be the sphere index buffer. Okay, well that's fine. Double checking, yep, seems fine. Let's close that down. So now all we need to do is in the prepare scene function, we need to write it to the buffers. So it's actually pretty straightforward, I would say. I'm just going to grab all of this code. Okay, so we go with the number of nodes which are used, and each of them has 8 floats, no worries. Let's go through here. Okay. This is going to be annoying, but it's not that bad. Okay, so it's min corner and then left child, and then max corner, and then sphere count. Okay, cool. Cool. So we write that in, and then we say write buffer. We want to write to the node buffer. We want to write the node data, and again 8 times the number of nodes used. Okay, see how that goes. Hey, who knows? It could throw errors. That's fine. I have a sphere index data. We're going to go with sphere count, but just 1 float for each of them. There we go, no worries. So we'll write to the sphere index buffer, just the sphere count. Okay, excellent. Okay. So the rest of this should be fine. I mean, we call this, we write the stuff, the shader consumes it, and I'm fully expecting errors, but we will work it out. Okay, so there's two things that I forgot. I hope it's just two things. One of them is in the case where we don't need to swap, fine, we increment the left counter. The other is in the case where we do swap, we need to decrement the right counter. And then the other thing is I've got this variable nodes used, but I never gave it any value at all. Let's just set it to 0. It was starting at not a number, and it's not good at all. So we'll just start that off. There we have it. Let's just... Okay. Okay. Right. Okay, so where I made the inverse direction, I just called that vec, not vec3. No problem. So just go over to the Raytracer kernel, and that should be vec3. Okay. What is up with this? Okay. When we swap things, that should be... Comment down below, are you having fun? Okay, let's give this a go. All right, no worries. Okay, so sphere lookup is object indices, and object indices has the array called sphere indices. Okay, now I really think this is it. I hope so. So this is not the number of floats, it's the number of bytes. So one float is 4 bytes. Okay. Finally, let's give this a go. Ah, nice. Okay. So as you can see, we are now rendering stuff, and we're doing it pretty quickly. So what I could do is we could dial up through all the different numbers, but let's just go to the maximum. So I think before we were doing like 1,000 milliseconds, more than 1,000 milliseconds for 8,192 spheres. Let's save that and see how quickly we can do it now with our acceleration structure. Now have a look at that. We've got a whole scene with a whole bunch of spheres, and we are doing it so quickly. We're doing it 5, 6, 7 milliseconds down from 1,000 milliseconds. If that doesn't sound exciting, I don't know what does. Look at that. And it's just beautiful. If we had lighting here, they would all be showing up nicely. So, yeah. Anyway, very cool, very satisfying to finally have it done. Anyway, I'm going to go grab dinner and then edit this together. So I hope you enjoyed this, and I'll see you again soon. Bye.